Hello, my name is Paul Geyer, and I'm here to chat with you about cathodic protection system maintenance. By way of introduction, this slide just tells you a little bit about what I've been doing for the last few decades. This discussion is going to be divided up into kind of two parts: scheduled preventive maintenance and unscheduled maintenance requirements. First, scheduled preventive maintenance. To comply with environmental regulations, public law, and industry standards, preventive maintenance is required for all installed cathodic protection systems. Maintenance actions in this section are the minimum required. First, with regard to close interval corrosion survey. The close interval corrosion survey is an interrupted potential survey on impressed current systems and a non-interrupted potential survey on galvanic or sacrificial anode systems. The purpose of this survey is to ensure that adequate cathodic protection is maintained over the entire protected structure. It should be thorough and comprehensive to identify problems within the protected structure or any interference problem on all foreign structures. The interruption cycle must have an on cycle of minimum duration 4 times longer than the off cycle, and the off cycle should not exceed 1 second. For surveys on galvanic systems, measurement errors must be considered typically through application of sound engineering practices which address the location of the reference cell, the protected structure, the anodes, the condition of the coating, the soil resistivity, and the depth of the protected structure. If test stations are installed at each anode, this also can be an interrupted potential survey. The minimum requirements for cathodic protection system testing of components should be in accordance with table 1.1 on this side. For galvanic or sacrificial anode systems, for each test station, 1 anode to soil potential measurement with the reference electrode placed over the anode and the anode lead disconnected. An anode to structure current test using, in order of preference, a clamp-on milliammeter, a multimeter measuring millivolts across a calibrated shunt, or a multimeter connected in series measuring milliamperes. For an impressed current system, perform a rectifier operational checkout. Calculate the rectifier efficiency by dividing the calculated output DC power by the factored input AC power, and perform the impressed current anode bed survey. Other scheduled preventive maintenance for other features are as described on this table: for pipelines, on-grade storage tanks, underground storage tanks, isolated structures, all structures with foreign line crossings, all structures with cased crossings, and all structures in soil. As part of the scheduled preventive maintenance, review all potential readings, annotate the low potential measurements, the high potential measurements, and other significant potential measurements to reevaluate those locations when performing the corrosion survey. If the data taken show that the current output is not sufficient, adjust or supplement the system as necessary. After 30 days, perform a corrosion survey for those locations identified in paragraph 1.3. With regard to the corrosion survey, this is conducted to ensure adequate cathodic protection still exists as proven on the last close interval corrosion survey. The procedures are the same as the close interval corrosion survey, with different minimum requirements for the potential measurements. The close interval corrosion survey data should be used to determine where potential measurements must be taken to reasonably ensure that the criteria of cathodic protection are being met for the entire structure being protected and no interference problems exist on any foreign structures. A corrosion survey should be conducted at the following intervals: 30 days after major modification to the cathodic protection system or the protected structure, after any corrosion leak on the protected structure, after any inspection or survey which indicates that the current requirement of the last corrosion survey are not valid, low or high potential measurements at the proper current output level, 1 year from the last close interval corrosion survey or corrosion survey which satisfied the owner's criteria. The minimum requirements using data from the most recent close interval corrosion survey or using sound engineering practices, choose a sufficient number of locations for potential testing to ensure the entire structure has adequate cathodic protection. Test the cathodic protection system components in accordance with Table 1.3 and Table 1.4 presents requirements for potential testing of the protected structure. Table 1.3 indicates the corrosion survey component testing requirements. Table 1.4 indicates the corrosion survey potential measurements to be taken for pipelines, on-grade storage tanks, underground storage tanks. The table continues with criteria for isolated structures, all structures with foreign line crossings, all structures with cased crossings, waterfront structures, other structures, and all structures. With regard to scheduled preventive maintenance, a review of all potential readings, annotate the 3 lowest potential measurements and the highest potential measurement to reevaluate those specific locations when performing the impressed current system check. For all structures, compare the potential measurements to those previously taken at the same locations to identify changes. If the potential measurements reveal current output does not satisfy criteria, adjust or supplement the system as necessary. After 30 days, accomplish the survey again. With regard to water tank calibration, the water tank calibration is a comprehensive and thorough survey to ensure that cathodic protection is maintained over the entire surface of the tank to be protected, and that there are no excessive voltages on any part of the tank interior that could damage the coating. Water tank calibration comprises an interrupted potential survey on impressed current systems and a non-interrupted potential survey on galvanic systems. The interruption cycle must have an on cycle that is a minimum of 4 times longer than the off cycle, where the off cycle is normally 1 second. On a galvanic system, measurement errors must be accounted for using sound engineering practices, including reference cell placement, anode positions, and coating condition. If the system design permits, this may also include an interrupted potential survey. Recommended intervals for conducting water tank calibrations are 30 days after the cathodic protection system is installed, modified, or adjusted, and 1 year from the last water tank calibration. Minimum requirements: inspection of the tank shall be in accordance with tables 1.5 and 1.6. Table 1.5 indicates water tank calibration requirements for a cathodic protection system component tests for both the galvanic systems or sacrificial anode and the impressed current systems. For the galvanic systems, measure anode to structure current using, in order of preference, a clamp on milliammeter, a multimeter measuring millivolts across a calibrated shunt, or a multimeter connected in series measuring milliamperes. For an impressed current system, A, perform the rectifier operational checkout, and B, calculate the rectifier efficiency by dividing the calculated output DC power by the factored input AC power. Table 1.6 gives water tank calibration potential measurements required for tank walls, tank bottom, metallic riser for elevated water tanks, permanent reference cells, and all tanks. For all tanks, compare potential measurements to measurements previously taken at the same locations to determine if changes have occurred. If potential measurements do not satisfy criteria and the current output meets the current requirement from the last survey, adjust or supplement the system as necessary. After 30 days, perform a water tank calibration test. Perform a rectifier operational inspection. The purpose of the rectifier operational inspection is to determine the serviceability of all components required to impress current to the anodes of the impressed current system. The inspection should be thorough to ensure dependable current until the next inspection. The maintenance intervals required, the checkout should be accomplished together with the close interval corrosion survey, the corrosion survey, the water tank calibration, or when any inspection or survey indicates that problems with the rectifier may exist. The minimum requirements: visually check all rectifier components, shunt box components, safety switches, circuit breakers, and other system power components. Tighten all accessible connections and check the temperature of all the components. Using a dependable handheld meter, measure the output voltage and current and calibrate the rectifier meters if present. For rectifiers with more than one circuit, measure the output voltage and current for each circuit using a dependable handheld meter and calibrate the rectifier meters if present. For rectifiers with potential voltmeters, using a dependable handheld meter, measure the potentials for each voltmeter and calibrate that rectifier meter. Using a known good reference electrode, measure the potential difference to the installed permanent reference electrode by placing both electrodes together in the electrolyte with the cathodic protection current off. If the difference is more than 10 millivolts, replace the permanent reference electrode. Calculate the cathodic protection system circuit resistance of each circuit by dividing the rectifier DC voltage output of each current by the rectifier DC ampere output for that circuit. For all close interval corrosion surveys, or if otherwise required, calculate the rectifier efficiency. This also includes timing the revolutions of the kilowatt-hour meter and annotating the meter factor from the face of the kilowatt-hour meter. With regard to the impressed current anode bed, the impressed current anode bed survey is a non-interrupted survey of the ground bed to determine the condition of the anodes. It should be comprehensive and thorough to identify any possible problem with the impressed current anodes. It may also be used to predict failure and to program replacement. This survey would normally be done together with the close interval corrosion survey. As a minimum, an impressed current anode bed survey should include on potential over the anodes at intervals described in Table 1.7, unless the system has incorporated other means for monitoring the anodes, for example, individual anode leads in an anode junction box. Table 1.7 provides recommended over the anode intervals for the impressed current anode bed survey, for remote shallow anode ground beds, for distributed shallow anode ground beds, and for deep anode ground beds. The impressed current system check is an operational check of the impressed current system to ensure the system is operating at the same level as the last close interval corrosion survey or corrosion survey. This is a non-interrupted check, and the potential measurements should be compared to previous on-cycle potential measurements. The locations for the potential measurements must be taken from the last close interval corrosion survey or corrosion survey, whichever is most recent, to reasonably ensure that the current output of the system is still being applied and is still sufficient. With regard to maintenance intervals, the recommended period for conducting the impressed current system check is within 60 days of the last close interval survey, corrosion survey, or impressed current system check. More frequent checks may be required by public law or regulations. Note that underground storage tank cathodic protection rectifiers must be inspected at a frequency not exceeding 60 days to ensure compliance with regulations. Check with state EPA authorities, as state regulations may be more stringent or may impose additional requirements. Measure the rectifier DC voltage and DC ampere outputs. Ensure that the DC ampere output of the rectifier meets the current ampere requirement found on the last close interval or corrosion survey. If necessary, adjust the rectifier output and measure outputs again. Repeat the procedure as necessary. Calculate the rectifier system circuit resistance by dividing the rectifier DC output voltage by the rectifier DC output current. If the rectifier has more than one circuit, calculate the resistance of each circuit. Take the SE potential measurements at the locations of the 3 lowest and 3 highest potential measurements identified in the most recent close interval or corrosion survey. Compare the potential measurements to previous measurements at the same locations and determine if changes have occurred. If potential measurements do not satisfy the criteria and the rectifier current output meets the current requirement from the last survey, adjust or supplement the cathodic protection system as necessary. Conduct a corrosion survey 30 days after adjustment or modification to the cathodic protection system. The galvanic anode system check is conducted to determine the operational condition. It's normally conducted as part of the close interval survey, corrosion survey, or water tank calibration surveys described in paragraphs 1.2, 1.3, and 1.4. The procedures to be used for the galvanic anode check: measure the potential of the structure with the reference electrode located directly over the structure adjacent to an anode, structure to earth, DC volts. Measure the potential of the structure with the reference electrode located directly over the structure, midway between anodes, remote structure to earth, DC volts. In this case, remote is as far as possible from the anodes directly over the protected structure. Disconnect the anode lead from the structure and measure potential of the anode with the reference electrode located directly over the anode, anode to earth, DC volts. Measure the structure to anode current, anode output current, milliamperes. Compare measurements to those previously taken at the same location. Loss of anode to earth potential indicates failed anode or failed anode lead. Loss of anode output current with stable anode to earth potential indicates consumption of the anode and pending failure. Loss of structure to earth potential with stable anode to earth potential and anode output current indicates loss of isolation. The resistance bond check is an operational check of 2 metallic structures connected with some type of semiconductor or resistor to ensure that the structures affected by the bond are maintained at proper levels and interference is mitigated. This bond may include reverse current switches, diodes, resistors, or other positive protective devices whose failures would jeopardize structure protection. These bonds may be between different sections of a protected structure or may be between a protected structure and any other metallic structure, unprotected or protected with a different cathodic protection system. This is a non-interrupted check, and the potential measurements should be compared to previous on-cycle potential measurements taken at the same locations. The locations for the potential measurements and meter connections must be the same, and the operational status of any cathodic protection systems must be known. The recommended period for conducting the resistance bond check is within 60 days of the last check or immediately following failure of the cathodic protection system, protecting either or both sides of the bond unless immediate repair of the failure is possible. More frequent checks may be required by public law or regulations. Minimum requirements to measure the rectifier DC voltage ampere output of the cathodic protection system on either or both sides of the resistance bond. Measure the DC current, ampere current flow through the bond and annotate the direction of the current flow. Measure the potential of the metallic structures on both sides of the bond. Evidence of proper functioning may be current output, normal power consumption, a signal indicating normal operation, or satisfactory cathodic protection levels on the structure according to the function or design of the bond. Compare the measurements to measurements previously taken at the same locations to determine if changes have occurred. If the potential measurements, current flow, current direction, or other measurement has changed from the last check, adjust or repair the component as necessary and repeat the test of the bond. The leak survey is a comprehensive, thorough survey to identify the cause of all leaks and the action required to prevent future leaks from occurring or to reduce the leak rate. The maintenance interval for leak surveys should be conducted after excavation, before backfilling of any leak on any pipeline or tank. Minimum requirements: measure the pH of the soil where it contacts the pipeline or tank. Measure the as found SE potential of the pipe or tank where it contacts the soil. As found means before any adjustments of existing cathodic protection systems, addition of any form of cathodic protection, or installation of isolation or bonding components. Determine the cause of the leak. Evaluate the condition and determine the appropriate repairs to the pipe or tank coating system. Measure the as left SE potential of the pipe or tank where it contacts the soil. As left means after all actions are taken to prevent future leaks. If these actions are taken after backfill operations, surface potentials are usually acceptable. If the leak survey determines the cause to be corrosion, determine the type of corrosion. Table 1.8 lists recommended corrective actions to prevent future leaks. Table 1.8 indicates recommended corrective actions for preventing leaks for structures not cathodically protected, for structures cathodically protected. Galvanic anode systems are typically used in low resistivity soil or on small or well-coated structures, or as hotspot protection on unprotected structures. Galvanic anodes may be easily installed before the backfill operation. Impressed current systems are typically used in high resistivity soil or on large or poorly coated structures. Also consider bonding to an existing impressed current system. Historical records should be maintained of all surveys and inspections for the life of the protected structure. This is important for maintaining proof of cathodic protection and for a reference for troubleshooting or repair of the system. Each cathodic protection system should have a folder with the following information on permit file: drawings of the cathodic protection system from as-builts or other sources showing the location of all components, drawings of the structure protected by the system showing all casings, foreign line crossings, test points, dielectrics, test stations, or other pertinent information, close interval corrosion surveys and corrosion surveys, water tank calibration records for water tanks conducted on the system, rectifier operational checkout records if an impressed current system is involved, impressed current anode bed surveys if an impressed current system is the one being investigated, impressed current system checks if an impressed current system is being investigated, and a leak survey data records for the structure protected. Any other pertinent data of historical significance, such as anode drawings, anode data, manufacturer data, source of supply, anode types, rectifier data sheets, wiring diagrams, manufacturer's data or manufacturer's manual, contract information, in-house drawings, or life cycle estimates or information. Now, moving on to Chapter 2, if you will, the unscheduled maintenance requirements. Some introductory comments. Impressed current cathodic protection systems require a higher level of maintenance than sacrificial anode or galvanic cathodic protection systems do. More things can and do go wrong. There are 5 major components to the operational impressed current system: the rectifier, the anode bed, the structure lead, the anode lead, the header cable, and the structure. There are 2 major components to the operational sacrificial anode system: the anode and the structure lead. If adequate cathodic protection does not exist on the protected structure, then troubleshooting must be accomplished to determine the cause of this lack of protective current. The starting point for all troubleshooting for impressed current systems is at the rectifier. Indications of all problems are present at this location. The greatest aids to troubleshooting are historical data and drawings of the system. Usually the fault may be isolated, then verified by testing. For impressed current systems, there are sufficient test points on the faceplate of the rectifier to isolate the fault component. Follow the troubleshooting procedures in paragraph 2.2, the typical rectifier wiring diagram, figure 2.2, the troubleshooting block diagram, figure 2.1, the shunt multiplication factor, figure 2.3, and the anode gradient samples, figure 2.6. The starting point for all troubleshooting for galvanic systems is at the anode or anode connection. For galvanic systems, there must be an anode test lead for conclusive testing of the anodes. For isolation of a fault to the major component, follow the troubleshooting procedures in paragraph 2.4. Troubleshooting of impressed current systems. First, a warning: all connections should be made with alligator clip leads with the rectifier circuit breaker or power switch off. If needlepoint leads are used with power on, employ electrical safety practices for working with live circuits. With regard to the DC voltage, measure the DC voltage output of the rectifier with a handheld multimeter. With power on scale on DC volts, measure voltage from N4 through P4, figure 2.2. One of three conditions may exist. Voltage may be near zero, in which case proceed to paragraph 2211. Nearly half of normal, proceed to paragraph 2212, or near normal, proceed to paragraph 2213. 2211, no voltage indicates that one of the components in the rectifier is faulty or there has been a loss of AC power. Proceed to paragraph 225. Half the normal voltage output indicates defective diodes, selenium plates, or improper AC input. Proceed to paragraph 225 to check the AC input to the stacks, and paragraph 227 to troubleshoot the diodes, selenium plates. Normal DC voltage indicates a break in the anode lead, failed anodes, or a break in the structure lead. Proceed to paragraph 22. If the voltage is normal and the rectifier voltmeter reads significantly different, the connections or the voltmeter are faulty. Proceed to paragraph 2213A. Warning: AC voltage is still present inside the rectifier with the rectifier circuit breaker or power switch off. All connections inside the rectifier cabinet should be made with alligator clip leads connected with the power to the rectifier off. If needlepoint leads are used with power on, use prudent electrical safety practices for working with live circuits. Figure 2.1 is a block diagram for troubleshooting. With power off, check for loose connections from P1 to P3, N2, and N5 through N7, including any press to test switch or button, and continuity of all wires between those points. This will require disconnection of AC power from the rectifier cabinet and possibly removal of the rectifier from the cabinet. Note that loose connections are characterized by heat, discoloration of the connection, and melted insulation. Repair or replace loose connections and replace damaged or broken wires. If problems are not found, proceed with paragraph 2213B. With power off, remove voltmeter from rectifier. This will require disconnection of AC power from the rectifier cabinet and possibly removal of the rectifier from the cabinet. Disconnect one end of the resistors on reverse side of meter. Measure the resistance of the resistors with a handheld multimeter on the ohms scale and compare to the value of the resistor. If no resistors are present, replace the meter. Replace resistor or meter as required. Figure 2.2 is a typical rectifier wiring diagram. Measure the DC current output of the rectifier with a handheld multimeter on the MV millivolt scale. Measure millivolts from N2 to N3. Multiply the indicated reading by the appropriate multiplication factor, figure 2.3. One of three conditions may exist. The current may be near zero, in which case proceed to paragraph 2221. May be near half of normal, proceed to paragraph 2222. Or be near normal, proceed to paragraph 2223. Figure 2.3 is the shunt multiplication factors. Normal DC voltage with near zero current indicates a break in the anode lead, failed anodes, or a break in the structure lead. Proceed to paragraph 223. Half the normal current output indicates either a defective diode selenium plate, a break in the header cable between anodes, or if there are multiple anode leads, loss of one anode lead or anode bed. Measure the DC voltage output of the rectifier with a handheld multimeter on the DC volt scale. Measure the voltage from N4 to P4. If voltage is also half of normal, proceed to paragraph 227 to troubleshoot the diode's selenium plates. If voltage is normal, proceed to paragraph 228 to troubleshoot the anode bed. If the current is normal and the rectifier ammeter reads significantly different, either the shunt, the connections, or the ammeter is faulty. Proceed to paragraph 2223A. If the current is normal, the rectifier ammeter reads normal, and structure potentials are still significantly changed from normal, proceed to paragraph 2223D. Measure the DC current with a handheld multimeter connected in series and with the meter on the DC amp scale. Disconnect the anode header cable at P4 and measure current from P4 to the anode lead. Compare the measured current value to the current value taken in paragraph 222. If values are significantly different, replace the shunt. If values are the same, proceed with paragraph 2223B. A word of warning: AC voltage is still present inside the rectifier with the rectifier circuit breaker or power switch off. All connections inside the rectifier cabinet should be made with alligator clip leads connected with the power to the rectifier off. If needlepoint leads are used with power on, observe prudent electrical safety practices for working with live circuits. With power off, check for loose connections from N2 through N9, including any press to test switch or button, and continuity of all wires between those points. This will require disconnection of the AC power from the rectifier cabinet and possibly removal of the rectifier from the cabinet. Note that loose connections are characterized by heat, discoloration of the connection, and melted insulation. Repair or replace loose connections and replace damaged or broken wires if problems are not found. Proceed with paragraph 2223C. With power off, remove the ammeter from the rectifier. This will require disconnection of the AC power from the rectifier cabinet and possibly removal of the rectifier from the cabinet. Disconnect one end of the resistors on reverse side of the meter. Measure the resistance of the resistors with a handheld multimeter on the ohms scale and compare to the value of the resistor. If no resistors are present, replace the meter. Replace the resistor or meter as required. Normal current values accompanied by loss of potential shifts indicate a change in the protected structure. If the protected structure is isolated, check all dielectrics and repair or replace faulty ones. If the protected structure is not isolated, check for additions to the protected structure or new structures in the area which are continuous with the protected structure, increase current to protect larger structures, isolate other structures, or install additional impressed current systems as required. With regard to the anode lead wires, with the power off, disconnect the anode leads to P4 using an alternative isolated metallic structure, isolated from the structure being tested. If doubt exists, measure continuity to the structure lead, such as a metal culvert or fence, or install temporary ground rods and connect to P4, the positive terminal. For a short period of time, turn power on and note AC current, paragraph 222. One of two conditions exists: either the current is now present, changed, or it is not present, not changed. Note: if the structure being tested is the inside of a water tank or tower and the lack of water will not allow flow, that is, there is no electrolyte, fill the tank and then retest. If current is present, if current exists, the anode lead is broken or the anodes have failed. Proceed to paragraph 228. If current is not present, if no current exists, the structure lead may be broken, in which case proceed to paragraph 224. With regard to the structure lead, for this test, the temporary or alternative anodes should remain connected to terminal P4 as described previously in paragraph 223. With power off, disconnect the structure lead at N4. Using an alternative isolated metallic structure, isolated from the structure being tested, if doubt exists, measure continuity to the structure lead, such as a metal culvert or fence, or install temporary ground rods and connect to N4, the negative terminal. For a short period of time, turn the power on and note the AC current, paragraph 221. One of two conditions exists: either current is now present, changed, in which case proceed to paragraph 2241, or it is not present, not changed, in which case proceed to paragraph 2242. Since current is now present, the structure connection is broken. Use the fault detector and cable locator connected directly to the structure lead at N4 to trace the structure lead from the rectifier towards the structure. This can be extremely difficult in some cases. An alternative method is to locate the first structure connection from drawings, markers, or induction methods, excavate to the structure, and measure continuity back to the rectifier using a cathodic protection multi-combination meter continuity check circuit. Use the fault detector and cable locator connected directly to the structure lead to trace the lead from the structure towards the rectifier. If this is still unsuccessful, replace the structure lead from the rectifier to the structure. Note that when using the direct connection method, it is essential to have a low resistance isolated ground for the fault detector or cable locator to put a strong locator signal on the cable under test. If current still does not exist, not changed, the temporary anode bed is not sufficient. Supplement the temporary anode bed, then repeat paragraph 223. 225, AC voltage to the stacks. Measure the AC voltage input to the stacks of the rectifier with, with a handheld multimeter on the AC volt scale. Measure the voltage from F6 to C6, the tap bars. One of two conditions may exist. The voltage may be near zero, in which case proceed to paragraph 2251. Or near normal, in which case proceed to paragraph 2252. 2251, when the voltage is near zero. This indicates loss of AC power to the rectifier, bad fuses or circuit breakers, or a bad transformer or connections in the rectifier, in which case proceed to paragraph 226. Paragraph 2252, voltage is near normal. This indicates faulty diodes or selenium plates or bad connections inside the rectifier, in which case proceed to paragraph 227. If the rectifier does not have taps, proceed to paragraph 226. If that test is normal, the rectifier must be removed from the cabinet for checkout. Prior to specific rectifier manual, refer to specific rectifier manual to troubleshoot the diodes or selenium plates and the transformer. For general reference, see paragraph 227 for the stacks and paragraph 229 for the transformer. Check all fuses and measure AC voltage input to the rectifier. With power off, remove all fuses at the rectifier and any fusible disconnect. Measure the continuity of fuses with a handheld multimeter. Set the scale to ohms. Measure the resistance of each fuse. Corrosion on fuse end caps or fuse holders will also cause loss of voltage. Replace any fuse with measurable resistance or clean and install fuses if corrosion is found. If a disconnect exists, measure the AC voltage with a handheld multimeter on the AC volt scale. Measure the voltage on the rectifier side of the disconnect. If a disconnect does not exist, measure the AC voltage from the circuit breaker of the rectifier with a handheld multimeter on the AC volt scale. For 110, 120 volt single phase rectifiers, turn power to the rectifier off, open the cabinet and connect the meter to A3, the output of the circuit breaker, and the ground, the cabinet. Turn the power to the rectifier on and the rectifier circuit breaker on. Measure the voltage from the rectifier circuit breaker. For 220, 240 volts single phase rectifiers, use the same procedures, but connect the meter to A4 and instead of ground cabinet, the output side of the circuit breaker on the second power lead, which is not shown on the drawing. If voltage is present, proceed to paragraph 2261. If voltage is not present, proceed to paragraph 2262. Paragraph 2261, when voltage is present, this indicates either the transformer or the connections inside the rectifier are faulty, and you should proceed to paragraph 229. 2262, when voltage is not present, this indicates the loss of AC power to the rectifier. Measure the AC voltage to the circuit breaker of the rectifier with a handheld multimeter on the AC volt scale. For 110, 120 volt power single phase rectifiers, turn power to the rectifier off, open the cabinet and connect the meter to A1 and A4. Turn the power to the rectifier on and measure the voltage to the rectifier. For 220, 240 volt systems, single phase rectifiers, use the same procedures, but connect the meter to A4 and the input side of the circuit breaker A1 on the second power lead, which is not shown on the drawing. If voltage is not present, proceed to paragraph 2210, or if voltage is present, replace the circuit breaker or fuse. Check the diodes or selenium plates of the rectifier with a handheld multimeter on the diode check scale. With the power off, remove the tap bars or shorting wires and the anode lead P4 and or the structure lead N4. Check the diode selenium plate sets by connecting one test lead to N4 and the other to F6, diode 3, then to C6, diode 4. Both should beep or not beep. Reverse test leads and repeat connections. The beep should be opposite. Both should not beep or beep. Repeat the test using P4 instead of N4 to test the diodes or selenium plate sets, diodes 1 and 2. Note that an ohm scale must be used. A good diode has very high resistance in one direction and low resistance in the other direction. With power off, check for loose connections from F6 to F7, C6 to C7, P1 to P2, P2 to P4, and N1 through N4, and the continuity of all wires between those points. Repair or replace loose connections and replace damaged or broken wires if possible. If no problems are found, replace the stacks. As to the anode bed, before a great deal of time is expended troubleshooting an anode bed, it should be determined from records if there is sufficient anode material to attempt locating and repairing the fault. Generally, if the current in time is calculated to amp years, comparing that number to the weight of the installed anodes and the weight loss of the anode material will indicate if the anodes are expended or have significant life remaining. Another indicator is if a gradual failure occurred over a period of time, the anodes have failed. If the failure was sudden, a cable break can be expected. If failed anodes are found, replace the anode bed. If a broken anode lead is found, repair the cable. The first step to locating the break is to find the location of any excavations that have occurred in the area of the anode cable. There are two methods of troubleshooting anode beds, depending upon whether all anodes have failed, there is no current, or some or most of the anodes have failed. If one or more anodes are functioning, see paragraph 2281. If no anodes are functioning, see paragraph 2282. If one or more anodes are functioning, the best method is first to locate the functioning anodes, then an anode bed gradient graph to isolate and locate the problem. Note that if separate anode lead wires in a junction box were installed, use these to measure the anode current and determine the functioning anodes. Perform a close interval survey over the anode bed. For the purpose of troubleshooting, you may adjust the rectifier to the highest voltage setting that would not result in coating damage to the structure to allow easier location of the anodes. Measure the potentials over the anodes with a handheld multimeter on the DC volt scale. With power on, connect the positive lead to the multimeter to the structure lead, N4, of the rectifier. Using a copper-copper sulfate reference cell connected to the negative lead of the multimeter, locate the point of highest voltage on the surface of the ground. This will be directly over an anode. Repeat by locating all operational anodes. Mark each anode found and compare to system drawings. Starting in a straight line 10 feet from the first anode, perform a potential test every 2 feet over the entire length of the anode bed to a point 10 feet past where the last anode is or is supposed to be located. Using a graph paper and using vertical lines to represent the measured potentials and horizontal lines to represent the 2-foot intervals, graph all readings. This will show the condition of all anodes and will indicate if a broken header cable, anode lead, or failed anodes exist. It will show a broken cable between functional and non-functional anodes. If anodes are failing, the gradients will peak differently, or the gradients will fall, then rise intermittently. If no anodes are operational, use the fault detector and cable locator connected directly to the anode cable P4 to trace the anode lead from the rectifier towards the anode bed. This can be extremely difficult in some cases. An alternative method is to locate the first anode from drawings, markers, or induction methods, excavate to the first anode, and measure continuity back to the rectifier using a cathodic protection multi-combination meter continuity check circuit. Use the fault detector and cable locator connected directly to the anode to trace the anode lead from the anode towards the rectifier. If this is still unsuccessful, replace the anode lead from the rectifier to the anode. Note that when using the direct connection method, it is essential to have a low resistance isolated ground for the fault detector or cable locator to put a strong locator signal on the cable under test. For rectifier taps, measure the AC voltage on the taps of the rectifier with a handheld multimeter on the AC volt scale. Remove the tap bars or shorting wires. Measure the voltage from F5 to F4, F4 to F3, F3 to F2, F2 to F1, and F1 to C1. All readings should be approximately the same. Measure the voltage from C5 to C4, C4 to C3, C3 to C2, C2 to C1. All readings should be approximately the same. Any lead that tests different must be checked for connection, in which case proceed to paragraph 2291. Note that on some rectifiers F1 to C1 may be a unique voltage. 2291 with power off, check for loose connections from F1 through F5 and C1 through C5, including any tap bar or shorting wire and continuity of all wires between those points. Note that loose connections are characterized by heat, discoloration of the connection, and melted insulation. Repair or replace loose connections and replace damaged or broken wires if possible. If only one tap is inoperative, a different tap setting may be operational, and testing will reveal functioning taps. If replacement of wire is not possible, replace the transformer. If no problems are found, proceed with 2292. Paragraph 2292 with power off, check for loose connections from A1 through A4 and continuity of all wires between those points. Repair or replace loose connections and replace damaged or broken wires if possible. If replacement of wire is not possible, replace the transformer. Note that the checkout of transformers or pole fuses requires personnel certified for work on high voltage lines and proper equipment beyond the scope of these procedures. With regard to the rectifier input voltage, first verify that the circuit breaker has not tripped or the fuse is not blown. If properly operating, measure the AC voltage from the circuit breaker or fuse where power is supplied to the rectifier with a handheld multimeter on the AC volt scale. For 110, 120 volt circuits, single-phase systems, open the circuit breaker panel or fuse panel and connect the meter to the output of the circuit breaker or the output side of the fuse, which is not shown on the drawing, and the ground or neutral bar. For 220, 240 volt systems, single-phase systems use the same procedures, but connect the meter to the output lugs of the circuit breakers or the output side of the fuses. If voltage is not present, proceed to paragraph 2210.1. If voltage is present, locate the breaker in the power feed from that point to the rectifier. Locate the break in the power feed from that point to the rectifier, circuit breaker, or rectifier fusible disconnect, whichever was last tested. 2210.1, measuring the AC voltage to the circuit breaker or fuse supplying power to the rectifier using a handheld multimeter on the AC volt scale. For 110, 120 volt single-phase systems, open the circuit breaker panel or fuse panel and connect the meter to the main lugs of the circuit breaker panel or the input side of the fuses, which are not shown on the drawing, and the ground. For 220, 240 volt single-phase systems, use the same procedures, but check individual legs separately. If voltage is not present, locate the circuit breaker panel or transformer supplying power to the panel and repeat paragraph 2210. If voltage is present, replace the circuit breaker or fuses. With the impressed current system, certain common problems. Table 2.1 lists those common problems associated with impressed current cathodic protection systems and the symptoms of those problems. And table 2.1 is presented here with symptoms and possible causes. For troubleshooting of galvanic or sacrificial anode cathodic protection systems, galvanic cathodic protection is inherently maintenance-free. The current is merely a result of the potential difference of the two metals. Recurring maintenance checks are performed to ensure continued satisfactory performance. Galvanic anodes sacrifice themselves to protect the structure. They normally consume themselves at a constant rate, and failure can be predicted by current measurement versus time. The most common problem in sacrificial anode systems are shorts around or failure of dielectrics on isolated protected structures. Due to the very limited voltage, sacrificial anodes usually cannot supply sufficient current to protect the structure if isolation is lost. On well-coated structures, the contact resistance to earth is high. Other metals in the earth that are not coated have a very low contact resistance, providing a low resistance path for anode current. Maintaining the dielectrics in an isolated system is essential to continued satisfactory performance of sacrificial anode systems. One failed dielectric can result in loss of protection for the entire system. Failure of the anode lead wires is common since copper exposed by nicks or insulation defects are cathodically protected by the anodes. However, these wires can be cut by extraneous excavations. Exercising control over digging permits in the areas of the anode ground beds may ensure that if the wires are cut, they can be repaired on site before backfilling occurs. Troubleshooting to locate the break at a later date is usually not successful, and replacement of a prematurely failed anode is more economical in almost all cases. A sudden zero anode current outbreak reading indicates probably failed lead wires. With regard to anode consumption, when sacrificial anode systems reach the end of their useful life, potential current and voltage measurements begin to change. When performing recurring maintenance, a significant drop in anode current indicates imminent failure of the anode. Potential measurements over the protected structure will begin to show dips or drops in the areas of failed anodes. A significant drop in anode potential indicates a failed anode. anode current may actually reverse after failure, due to the copper center tap of the anode being cathodic to the protected structure. When drops in the potential of the protected structure begin to occur, a closer inspection should be made to determine the extent of the damage to the anodes. Except on small or extremely well-coated structures such as underground storage tanks or short pipelines with butyl rubber or extruded polyethylene coatings, it is normally not economical to replace a distributed galvanic anode system. When galvanic anodes begin to fail on a distributed system, impressed current cathodic protection should be considered. With regard to interference testing, although impressed current cathodic protection systems overcome all of the shortcomings of galvanic cathodic protection systems, there are problems. The two main problems are that impressed current cathodic protection systems require a higher level of maintenance, and there is a possibility of interference corrosion on other metallic foreign structures. Interference corrosion is the most serious form of corrosion. When a metallic structure experiences interference corrosion, 9.4 kilograms, 20.7 pounds of steel is transformed to iron oxide for every ampere of current which flows for 1 year. For a coated pipeline, this current is leaving from the holidays and the time to failure is extremely short. Whenever signs of interference corrosion are noted on any scheduled maintenance or leak survey, emergency steps must be taken to preclude further damage to the structure. With regard to interference corrosion control, whether caused by the influence of cathodic protection systems or by other current sources, it can be effectively controlled. Examples of typical corrective actions are presented to illustrate some of the methods employed and to show how to perform field measurements to determine the continued effectiveness of the corrective measures. Correction of actual interference problems is beyond the scope of this manual. Correcting interference. One method of correcting interference is to bond the foreign structure to the protected structure. Thus, both are protected. Figure 2.4 shows correction of an interference problem by bonding. A test station is usually installed at such a location to either verify the continuity of the bond or to measure the current flowing through the bond. Extra wires to each structure allow potential testing of individual structures using a non-current carrying conductor, which results in a 4-wire test station. Current measurements are normally taken using a calibrated shunt. Other methods include using a clamp-on ammeter or milliammeter, or disconnecting and measuring in series using a low input resistance ammeter. Direct bonding is often not desirable either because the existing cathodic protection system cannot supply enough current to protect both structures, or the foreign structure is not owned by the same organization as the one supplying the current, and the minimization of extra current is desired. In this case, a resistive bond is installed between the structures and adjusted so that only that amount of current is supplied to the foreign structure which is required to bring its potential to the same level as it would have been without the interference present. Figure 2.4 shows such an installation. Test stations are normally installed where resistive bonds are used in order to facilitate testing of the corrective action and adjustment or replacement of the resistor. Direct bonding usually is not possible if the protected structure is well coated and the foreign structure is bare or poorly coated. Resistors may fail due to substantial interference currents and the possibility of surges or fault currents. If failure of the resistor would result in loss of adequate protection to a structure that requires cathodic protection, the resistance bond would be considered a critical bond. Critical bonds must be tested on a recurring schedule of not less than 60 days. With regard to continuity, bonding, as shown in Figure 2.5, is also used to ensure continuity of buried structures, both for the prevention of interference and for proper operation of cathodic protection systems. Installation of a sacrificial anode. In some cases, interference is controlled by installing a sacrificial anode or anode bed on the foreign structure to raise the potential of the foreign structure and provide a lower resistance path for discharge current to flow from the installed anodes instead of the foreign structure. The use of a sacrificial anode to control interference is shown in Figure 2.6. This method normally works well when the interference current is fairly low and the foreign structure has a relatively good coating. This method may be combined with coating the cathode, the protected structure, near the discharge area to lower the interference current. Figure 2 indicates the correction of interference by resistive bonding. Protected structure indicated on the left, foreign structure on the right. Figure 2.5 indicates bonding for continuity. Figure 2.6 indicates the use of galvanic anodes to control interference. Additional coating to the protected structure in the area of the current discharge on the foreign structure raises the resistance of the stray current path, reducing the magnitude of the interference current. This method will usually just lower the interference current and is used with other methods to stop interference. When the interference current levels are very low, this method may be adequate to stop the interference. Although normally used at pipeline crossings, this method could apply to any interference problem. During the installation of a protected structure, additional coatings can be easily installed in areas where stray currents may be expected. For example, at all foreign pipeline crossings or foreign structure crossings, such as metal fences, metal culverts, and electrical grounds. During installation of a butyl rubber or similar mastic in combination with extruded polyethylene, it may be used on the protected structure in those areas. As a retrofit to an existing structure, a primer and tape wrap system may be used, with the additional requirement to excavate and clean the protected structure. This method of interference control is most economically used during the design and installation of the protected structure. As an alternative to applying additional coating, non-conductive barriers are sometimes used between crossing pipelines for similar reasons. Barriers do not require uncovering, cleaning, and coating the protected pipeline if it is sufficiently deeper than the foreign structure and may be more economical in some cases. Barriers must be much larger. Coating the protected structure for 40 feet on each side of a foreign pipeline crossing would be as effective as an 80-foot diameter barrier. This method of interference control is most economically used during the design and installation of the foreign structure. Figure 2 indicates the use of the coating of the cathode to control interference. Installation of non-metallic sections or isolations on the foreign structure in the stray current pickup area and between the pickup area and the discharge area may significantly reduce the amount of interference current by substantially raising the resistance of the stray current path. This type of action is usually adequate for metal fences. By isolating sections of fences using two non-contacting fence posts, wooden fence posts, or dielectric materials between the fence hardware and the fence posts. Isolations can be made in the current pickup area and between the pickup area and the discharge area, sometimes supplemented with a sacrificial anode in the discharge area. This may be considered as part of a design for an impressed current installation if there is a continuous metallic fence in the area where an impressed current anode bed is to be installed, or if a metallic fence is to be installed in an area with an existing anode bed. Figure 2 indicates the use of isolation on foreign structures to control interference. For interference problems which are more serious and where bonding or resistance bonding is not possible or practical, consider the application of a small impressed current system on the foreign structure in the discharge area to protect the foreign structure from stray current corrosion. As shown in figure 2.6, substituting a rectifier and impressed current anodes for the sacrificial anodes, the corrosion is stopped by the application of sufficient cathodic protection to the discharge area. Caution should be used to balance the two systems, since this installation may interfere with the original protected structure that was causing the stray current corrosion. In many cases, a combination of the preceding mitigation techniques may be prudent. The magnitude of stray current, the soil resistivity, the protected structure coating efficiency, and the foreign structure coating efficiency, and the type of foreign structure should be considered to ascertain the most cost-effective choice for mitigation techniques. Figure 2.9 indicates the use of a combination of mitigation techniques to control interference. And that brings us to the conclusion of this discussion of cathodic protection system maintenance. I hope that this has been of interest to you and helpful, and that it will be of some value to you moving forward as these types of challenges come across your desk. So thanks a lot. Have a nice rest of the day.